18B. A coin is tossed 10 times. The probability histogram for the number of heads is shown at the top of the next page with 3 different shaded areas. One corresponds to the chance of getting 3 to 7 heads inclusive, one corresponds to the chance of getting 3 to 7 heads exclusive, and one corresponds to the chance of getting exactly 6 heads. Which is which? So number 1 would be exactly 6. Number 2 would be 3 to 7 exclusive. We're not counting the 3 column and we're not counting the 7 column. And 3 would be 3 to 7 inclusive. We're counting the 3 and the 7. Does everybody understand the difference? No? So look at this table. Okay. So this is the number of heads that could happen. If we flip a coin 10 times, how many heads do we expect? 5. So this right here is 1, 2, 3, 4. 5 is marked. 6, 7, 8, 9. So I play the game and I get 2 heads. You play the game, you get 6 heads. Somebody else plays the game, they get 7 heads. We want to know the chance of getting each one. Well, here's the probability histogram. Okay. Which one represents how many times people who played the game got 6 heads? That would be this column. That's how many, that is, the area is the chance of getting 6 heads. Okay, and then what does this one represent? It added up the 4 and the 5 and the 6. So we could either say 4 to 6 inclusive, or the book called it 3 to 7 exclusive, meaning everything between 3 and 7 and 3 and 7 don't count. And then the next one, this is, we're adding up the 3, the 4, the 5, the 6, and the 7. So this is 3 to 7 inclusive, meaning the 3 and the 7 are part of the answer. So how would we calculate z-scores for 3 to 7 inclusive? What would the left bound be? 2.5. What would the right bound be? 7.5. What if we went to the middle graph? What's the left bound? 3.5, and the right bound? 6.5. Yeah. Okay. All right, next question. In figure 3 on 315, the chance of getting 52 heads exactly is exactly equal to the area between 51.5 and 52.5. Okay. Under the not normal curve, probability histogram. We're adding up the probability histogram, which is the expected. We're not doing the, I mean, we could do normal curve, but actually, you can do both, right? Yeah, okay. But that, I mean, we know how to do it both ways. So, okay, number 3. A coin is tossed 100 times. Estimate the chance of getting 60 heads. So what is the expected value? 50. And we already know that the SE is 5. So what's the chance of getting exactly 60 heads? Well, we have to find the area between 59.5 and 60.5. And before, we didn't have any way of doing this. Before, we could find the area between two numbers, but we couldn't find the area for a single number. So we have a 50 here and 60. So we want to find the area between 59.5 and 60.5. Okay, well, how big is that? 10.5. And how big is this? 9.5. What do I do with those numbers? Divide them both by the SE. So you're going to get 2.1 and 1.9. Now what do we do? Shade norm. So clear my draws. And then I need to go to my zoom recall. And then shade norm. Sorry, I've got a graph in there I need to get rid of. Two graphs. Okay, so shade norm from 1.9 to 2.1. And we should end up with an area to the right that's just a little sliver, and I get 1.08%. Yes, that's the chance of getting 60. It was 1%. Yeah. Carrick's data on 10,000 tosses of a coin can be taken in successive groups of 100. About how many groups should show exactly 60 heads? 1%, which is how many? If we do so, if we take the 10,000 tosses and we divide it up into groups of 100, how many groups will there be? 10 times 100 is only 1,000. 100. So 10,000 games can be divided up into 100 blocks of 100. Okay, so in game 1, we might get like 51. And in game 2, we might get 48. And in game 3, we might get 50. And so on. How many games are there of 100 tosses in a 10,000 toss set? 100. So this goes all the way to 100. Do you get that? Are you okay with this, Alexis? So if we went out and got 100 kids and everybody flipped their coin 100 times, and the first person got 51 heads, second person got 48, and so on, how many of those would we expect to get exactly 60? 1% of them, and how many games are there? 100. 1% of 100 is 1. We would expect one person to get 60. If 100 people tossed a coin 100 times, one person should get 60. Okay, would it be exactly 1? It could be 0, it could be 2, it could be 3, but the more you play, the more you're going to get closer and closer to 1%. Okay, a coin is tossed 10,000 times. Estimate the chance of getting from 4,900 to 5,050. So, in our histogram, 4,900 and 5050. Okay. We're going to look at this box. What's the left side of that box? 4, 9, 4, 8, 9, 9.5 to 5050.5. Okay. So this is 50.5, and this is 100.5, right? The expected value should be 5,000. So that's 100.5. So we divide those. 50.5 divided by 5 gives us an upper bound of 10.1. And then 100.5 divided by 5 gives us a lower bound of 20.1. What do I do with those? Not yet. Oh, yeah. Yeah, we do shade norm. Oh, it's not 5 anymore. Sorry. It's 1/2 times the square root of 10,000, which is 50. Okay. Yeah. that will definitely be a better number. So 50.5 divided by 50 is 1.01, and 100.5 divided by 50. So I need to find the shade norm between negative 2.01 and 1. Okay. So shade norm, negative 2.01 up to 1.01. And that gives me 82%. Now, before today, we didn't care about the endpoints, right? Before today, we would have just said up 50 and down 100, and we would have plugged in negative 2 and 1. Does it make that much difference? So shade norm from negative 2 to 1. So I was at 82%. And now I'm at 81.8. Does it matter? No, because these numbers aren't perfect anyway. Yeah. Okay. So 4,900 heads or fewer. What would you plug into your shade norm? So let's clear the draws. So we're going to go from negative 5, yeah, or that number, up to, do we want to include 4,900? It says 4,900 or fewer. Yes, so we actually need to go negative 1.99, because it would be negative 100 would be 2 SEs. So if we go up 0.5, that's 1/100th. So it would be negative 1.99. It wouldn't even give me that. Oh, my draw didn't clear, but we'll get the percentage of 2.8%. Okay, 5,050 or more. So now we're going to include this number here. So that would be 5049.5. So 49.5 divided by 50 is going to be 0.99. 0.99 to 5. Oops. So from 0.99 to 5. And we end up with 16%. Okay, 6. Suppose you were going to estimate the chance of getting 50 heads or fewer in 100 tosses of a coin. Should you keep track of the edges of the rectangle? So, what do we expect to happen? Would we say exactly half should be 50 or fewer? And the answer is go back to, so turn back. Do we have do we have histograms for 100 tosses? Yeah, bottom of 315. Okay. 50 or fewer. Would that be exactly 50%, slightly larger, or slightly smaller? If I said you're going to play a game where you flip a coin 100 times, is it a good idea to play the game if you win if you get 50 or fewer? Yes, because you're going to be slightly larger than 50%, because 50 wins, right? If I said less than 50, should you play that game? No, because 50 is a losing number. So I guess let me show you what it's asking. All right. The chance of getting 50 or fewer is this area here. Is that half of what's up there? It's slightly more than half, right? Because half would be right here. But 50 counts. So your odds are slightly higher than 50%. Or sorry, your probability is slightly higher than 50%. Okay, your odds would be just a little bit larger than 1. So yes, you would want to count the endpoints because then you would end up with a slightly larger probability. Is that the last question?